are gonna solve a differential equation, and for that we have dy upon dx plus y cos x plus sin y plus y whole upon sin x plus x cos y plus x equal to 0. Now guys, to solve the differential equation we have many methods with us. So we may use the variable separation method, or we may use the other methods which are present in the differential equation. So let's start with one method. So if I am planning to apply the method of variable separation, then it is almost difficult to separate the x and y on both sides. So what we will do is we will check whether the given differential equation is exact or not. So if it is exact, then we'll solve by exact differential equation, and if it is not exact, then we will reduce it to make it exact, and then we will solve it by the method of equation reducible to exact method. So let's start. So to check whether it is exact or not, according to rule, we have to bring it in the form m dx plus n dy equal to 0, and then we check the condition of exact differential equation. So guys, for that I'm doing the cross multiplication. So here, by multiplying these two terms, we will get sin x plus x cos y plus x into dy plus y cos x plus sin y plus y dx upon multiplication of these two terms. Those terms will go on the right hand side and we will get 0. So here we'll compare this equation with m dx plus n dy equal to 0. So now comparing with this form, we can say that m is a term which is with dx. So here with dx we have this term. So m is equal to y cos x plus sin y plus y, and n is a term with dy. So it is equal to sin x plus x cos y plus x. Now to prove that the given differential equation is exact, we have to prove the condition, that is the value of dou m upon dou y is equal to dou n upon dou x. So guys, let's find it out. So here I'll say therefore dou m upon dou y equals to, so for that I'll partially differentiate m with respect to y. So here cos x, or the terms of x, will be treated as constant. So cos x is constant, derivative of y with respect to y is 1, plus derivative of sin y is cos y, and the derivative of y is 1. Next we'll find out dou n upon dou x. So here sin x will give us cos x, then cos y is constant because I'm partially differentiating with respect to x, so plus cos y as it is. Derivative of x with respect to x is 1, so here we'll get 1. And guys, now if you'll see these two values, then they are exactly same. So dou m upon dou y is equal to dou n upon dou x. And whenever this condition is satisfied, we say the given differential equation is exact. So since the given equation is exact, we can get the solution of this differential equation by the method of exact differential equation. So what is the formula? So the solution of such exact differential equation is given by any one of these two formulae. So guys, here you can see that first formula is integration of m dx by treating y terms as constant plus integration of n by treating or by considering the terms which are free from x with respect to y. So here I'll say, therefore its solution is given by integration of m dx. So what is the value of m? So this is the value of m. So I'll say y cos x plus sin y plus y into dx plus integration of n dy, and in the end we have to consider the terms which are free from x. So guys, here this n has three terms and all three terms has x, so there is no term which is free from x. So here I'll say directly it is 0 dy equals to c. Now let's integrate this. So I'll treat y as constant as said in the formula. So y as it is, integration of cos x is sin x plus integration of sin y. So sin y is constant outside and integration of 1 is x plus again y constant and integration of 1 is again x equal to c. So guys, this is the solution of given differential equation. So here we have learned how to solve the differential equation by the method of exact differential equation. So I'm sure that you like this video and you want to learn more such videos on engineering mathematics and differential equation. So guys, you just have to log into ekeeda.com for that and you can watch unlimited videos at one place. Thank you very much.